Math 1325, we are in the middle of a 3-day review for the final. Previous video we did problems 1 through 10, and today we're going to be doing 11 through 20. The next video will be 21 through 30. That helps to break it up a little, so it's a 2-hour final. Takes probably about 2 hours to do the review. Break it up into 3 parts so that you can practice and concentrate more easily. Then save 1 day for doing a full practice run before doing the actual final. So let's pick up where we left off last time. We're now up to number 11. For the given function, a, find the equation of the secant line through the points where x has the given values, and then find the equation of the tangent line. So f of x equals x squared plus x. And the two given spots are 1 and 3. Okay, so when x is 1, 1 squared is 1 plus 1 is 2. So the function goes through 1, 2. When x is 3, 3 squared is 9, plus 3 is 12. So let me just mark a spot off here and call that 12. 3, 12. So this is a parabola that goes through 0. Curved like that. It also would go through -1, but that we don't really care about right now. So we have this parabola like this. And then especially if I blow this up, let's go from 1, 2 up to 3, 12 and put a little bit of a bend on this right there. So here's 3, 12. Here is 1, 2. And then the rest of the graph's like that. So what we first care about is a secant line is a line that goes through a curve twice, like this and that. Let's keep that going forever up. So what's the equation of this line? Well, the equation of a line is y equals mx plus b. And we can easily find the m by doing the slope formula. y2 minus y1 over x2 minus x1. So I'll just call this the first x, first y, second x, and second y. So 12 minus 2 over 3 minus 1. That's 10 over 2 or 5. The slope is 5. Then I can choose either 1 and 2 or 3 and 12, but not you can't choose 1 and 12 or 2 and 3. You can't have a mixture, but you can choose either one. I'm going to choose 1 and 2 and just temporarily plug 2 in for y and 1 in for x. 2 equals 5 times 1 plus b. And 5 times 1 is 5. Subtract 5. 2 minus 5 is -3. So the equation of the secant line is 5x minus 3. Y equal, they already have the y equals here, 5x minus 3. Then find the equation of a tangent line where x has the first value, because that's important since there would be a different tangent line at the other spot. So a tangent line crosses a curve and touches it just at that one spot only. So just from my sketch, I can tell it has a little bit flatter of a slope. So here's where the calculus side comes into this. The equation of a secant line is basically algebra because you're just using slope. The equation of a tangent line, the slope of a tangent line is the concept of derivative. So if I can easily find the derivative, although maybe when we learned this back then, you had to go through the long process of doing the derivative, but at least now in the final, you can take the shortcut and just use the power rule, 2x plus 1. The derivative of x squared is 2x, the derivative of x is 1. So what's the derivative when x is the first of the two given values, 1? It would be 2 times 1 plus 1, or 3. So the tangent line is going to come like this, if I drew it better, and touch it exactly there, just once. It won't go through the curve twice. So y equals 3x plus b. And now I don't have a choice. I have to use that coordinate 1, 2, although I would pick that one anyway. We have to plug in 1, 2, because that's literally the only time we're touching the curve. So no choice there. The x has to be 1 and the y has to be 2. 2 equals 3 times 1 plus b. 3 times 1 is 3. Subtract 3. And b equals -1. So all that means is if you followed this line and went back to the y-intercept, it would cross the y-axis at -1. And the other one would cross at -3. This is -3 right here, and this is -1 right there. So you can even see that in the sketch of the graph, how the slope definitely seemed less steep for the tangent line, and then it crosses the y-axis a little bit higher up at -1 instead of -3. So it's not a guarantee I did everything right, but at least based on the sketch I drew, these both seem like reasonable answers. Okay, see, I think that was actually taught right before they taught you guys how to do the power rule. So it was actually done a lot. It would take a lot longer to do problems like that, but they wanted you to understand what was going on first. So now this is the first time the power rule is actually employed. And it's a little more challenging if you have fractional or decimal or negative exponents. So I'll do that a little slower than if it was the easier one that we had a second ago. But there's a -10 x to the -2/5 plus a 16 x to the -3/4. So derivative power rule, you do the exponent times the constant first. Exponent times a constant, -10 times -2/5. You could reduce the 10 into the 5, leaving you 2 for a division. And then -2 times -2 would be +4. The x stays the same. And then you decrease the exponent by 1. Subtracting 1 minus 1. But 1 is the same thing as 5/5. So that way there'll be a common denominator. So -2/5 minus 1 or -2/5 minus 5/5 is -7/5. And then technically you're multiplying by the derivative of the base, but the derivative of x is just 1. So that's the chain rule always applies even when you just have an x here. It's just we're multiplying by 1, so we basically ignore it. But if the base was anything other than just an x, then we'd have to chain on the derivative of the base. So 4x to the -7/5. And then I need to multiply 16 times 3/4. Or was that, let me see if that was negative. See, I almost had a brain crap mistake. It was -3/4. I thought I remembered saying negative, but I didn't write it for some reason. So -3/4. 16 goes into 4 times. 4 times -3 is -12. And then take your -3/4 exponent and subtract 1 or subtract 4/4. So that would be -7/4. And both of the bases are just x, so this is it. So using the power rule, the derivative of the original function is 4x to the -7/5 minus 12x to the -7/4. 4x to the -7/5. 4x to the -7/5 minus 12x to the -7/4. The second thing we learned in the derivative chapter is the product rule when I have a function of x times another function of x. So number 13. Two x squared plus 5. This is considered to be the first function times 3x minus 2. That is the second function. So product rule again is first times derivative of the second plus the second times the derivative of the first. So I'm going to leave the first function as is, 2x squared plus 5. The derivative of the second, if that was my entire problem, if I just had 3x minus 2 and they said find the derivative would be 3 for this part and 0 for a constant. So the derivative is just 3. And then I leave the second function alone. Derivative of the first, you would just, this is a polynomial, you would just do it term by term using the power rule. 2 times 2 is 4x to the 2 minus 1, which is 1, plus 0. Then I can distribute this and get 6x squared plus 15. Here's a 12x squared and a negative 8x. So there's a couple of like terms. 6x squared plus 12x squared is 18x squared. Then I would put the minus 8x second and the plus 15 last. 18x squared minus 15x plus, maybe I said that wrong, that was minus 8x plus 15. I knew there was a 15 in there somewhere. Negative 8x plus 15. Now another thing about this problem is, what if I would have FOILed out the original problem? What if I would have got 6x to the third minus 4x squared plus 15x and minus 10 using FOIL. First, outside, inside, last. So I used FOIL to multiply out this two polynomials multiplied together, and that's doable because they both had to the first power here. But if these were anything other than first powers, then you wouldn't be able to do it so easily, and maybe not even really at all. If these were like 7th power, 8th power, 20th power, then certainly you wouldn't want to multiply them out. But since they were both first power, it was real easy to multiply them out. And then I could just do the power rule, because this is a long polynomial term by term. The derivative of 6x to the third is literally 6 times 3, 18. Decrease the exponent by 1 to a 2. And then the derivative of negative 4x squared is 2 times negative 4, negative 8. Decrease the exponent by 1 to a 1. And the derivative of 15x is just 15, and the derivative of negative 10 is nothing. So yeah, I just double checked that that answer is definitely correct. 18x squared minus 8x plus 15. I did it by 2 different methods and got the same answer both ways. Now, quotient rule, you don't really have a choice, because in theory, maybe you could do long division and try to simplify this out, but this isn't going to divide nicely. So it's kind of like a fraction that's fully reduced. There's no way to divide it. This I could multiply, but this next problem, there's no way to divide. So now you don't really have a choice. Sometimes there isn't a choice in doing it 2 different ways. Sometimes there is in math. In math, there is often 2 different ways to do problems. And then you could pick the easier way once you get comfortable with both of them. But sometimes there's only one way to do it. This can only be done with the quotient rule. So the quotient rule has 3 differences compared to the product rule. The product rule we learned first, and that's where you do the first. The quotient rule is learned second, so that's why you start with the second first. That's the first difference. The product rule starts with the first, the quotient rule starts with the second. And then there's always an alternation going on. You're doing first, and then you're switching to the second, and there's a derivative. Then you have the second, and then you have the derivative of the first. So you need one of each of these four things. I have a regular first, I have a derivative of the first, I have a regular second, and a derivative of the second. The same thing happens here. So if you've already done the second, you need to be doing the derivative of the first next. And then we need the first, since we already have a second. And then that needs to be multiplied by the derivative of the second. So that way I've got a regular, a derivative, a regular, and a derivative. That always alternates. And then I have one of each thing here. So once you know which one starts first, then the rest kind of fall in domino order. That's usually easy to remember. And which one goes first is important, but that's easy to remember because we do multiplication before we divide normally anywhere in math. And then the product rule is associated with plus, which makes sense because remember the rules of exponents: when you multiply powers, you add exponents. When you divide powers, you subtract exponents. So that makes sense that the product rule has plus and the quotient rule has minus. That's the second thing that's different about them. The third and final thing that's different is the quotient rule also has a denominator where you do the second squared, although that's usually easy. Usually you square the denominator and it just stays in the answer the whole way. So I'm going to have this 7x plus 9 in the denominator squared, and it's probably going to be part of the answer. And if it takes me 3 or 4 steps to do the numerator, it's okay. The denominator will just keep repeating all the way down. Okay, so second is 7x plus 9. The derivative of the first is easy because it's a linear piece, so you just do the derivative, would be 3. Now I'm going to rewrite the first function exactly as it is. And the derivative of the second is just 7, since that's linear as well. So then I could distribute and put any like terms together. So this is going to be a 21x plus a 27. This at first is 21x minus 7. But there's a minus here, so you got to put this minus on both parts actually, not just the first part. So it's negative 21x, but positive 7, not negative 7. And here we get lucky that the 21x's cancel. That doesn't always happen. And then 27 plus 7 is 34, not 20. So a very common mistake is to put 20 here instead of 34. And I'm rewriting the denominator squared, so this is the answer since the top is just 34. Potentially, if the top didn't have the x's cancel, and if I was somehow able to factor out, if I could get a GCF from the numerator and then somehow get a 7x plus 9 left over, in rare cases that does happen sometimes. If that were to occur, only if that were to occur, then this would cancel the square of that. And you would have to do it or they would count it wrong. That's the only way the denominator squared isn't in the answer. But probably 95% of the time, if you make up your own quotient rule problem to do, usually 95% of the time, once you square the denominator, it just stays all the way till the answer. Most of the time, the numerator can't even be factored. And if it, in the rare cases when it can, it often doesn't even have the denominator's factor in it. So if you're able to factor the numerator, but it doesn't help you to get a 7x plus 9, then you don't have to factor it actually. But you have to look and just make sure that in a rare case, possibly, make sure that there can't possibly be a 7x plus 9 on the top. As long as you can know that that's for sure not going to happen, then you don't have to worry about simplifying the numerator more than whatever we just did to it. Okay, and then the third thing that you basically, well, actually the fourth thing, you got your power rule first. That's the most basic rule of derivatives, power rules. Then we learn product and quotient kind of in the same section. And then the next thing on the list was the chain rule, which really could have been taught right away and could have been going on all along. But now I've got k of x equals -6 times 3x squared plus 7 to the -6 power. So basically what this is if you had y equals -6x to the -6. What if this big parenthesis part was just an x? Then it would be a power rule. -6 times -6 would be +36. The x is rewritten, and then you decrease the exponent by 1 to -7. And then technically you're multiplying by the derivative of the base. The derivative of x, since x is just linear, is 1. The chain rule has always been going on even when they first taught this power rule. So this works very similarly, except the derivative of the base is something other than 1. So -6 times -6 is 36. And then you rewrite the base because you got to decrease the exponent by 1. So the base, nothing happens to the base at first until you decrease the exponent by 1. And then the chain rule says the derivative of the base also is included in a derivative. And the derivative of this is different than 1. It's actually 6x to the first. So then it gets chained onto the answer. But it really happens all the time, even when it's a 1. It's just we ignore it when it's a 1. So then you don't want to touch anything that has a parenthesis with an exponent other than a 1. So I can't like distribute into this parenthesis or try to multiply this out. So often that's just going to get tacked on to the end of the answer. Whenever there's a parenthesis part to an exponent other than a 1, you just leave that in your answer. But the regular 6x could be multiplied to the 36 to get 216x. And it just makes it look better if you do that. They might count the answer right if you left it like this. But it's better to clean it up so it looks better. 216x looks better than a 36 and a 6x. The 6 and the 36 can go together. You could alternatively put the negative exponent in the denominator, but that's usually not necessary either. If I was going to be plugging x's in, like I was going to do k prime of 7 or something, then it would be better to do this. So that's why it's good to know that that's a possibility, and they would accept this answer too. But it's usually an unnecessary step that you're just wasting time and taking a chance you might make a brain cramp mistake if you do extra stuff that you don't need to do. So I'm not plugging any numbers in for x, so I would leave the answer like this. It's the most simplified version. It's a little better in my opinion than this answer. At least it's simplified, but I don't have to worry about the negative exponent. If I'm plugging numbers in, I would want to have a positive exponent. It's just easier to calculate things with positive exponents than negative. But I'm not plugging any x's in, so I don't need to do that. 216x. And then you get your 3x squared plus 7 base. And then that's getting decreased to the -7th power. 216x and 3x squared plus 7 to the -7th power. Okay, so that was 4 types of derivatives. The 5th and the 6th type are exponentials and logs. So the rule for exponential, those are the nicest ones of them all, because the derivative of an exponential is itself at first. So 5e to the 4x squared. The derivative of an exponential is itself. That's the nice part about it. And then there's possibly 2 adjustments to make. If the exponent is anything other than an x, then the chain rule applies. So then I'm tacking on the derivative of the exponent, which here is 8x to the first. But if the exponent is just x, then the derivative of that is 1, and then it's like it doesn't matter. But that's really the chain rule that can happen on any problem. So I did the derivative of the exponential was itself at first, times the derivative of the exponent, and then technically you're multiplying by ln of the base. But many times the base is e, and ln of e equals 1. So if you get base e, then this doesn't matter, if there's other stuff still here. But if it was any other base besides an e, then I would have to have an ln of that base multiplied on. It's just like an extra constant to the problem. So again, they probably would take this answer, but I'm going to clean it up and do 5. Why not do 5 times 8? It just looks better. That's easy. 40x e to the 4x squared. Especially if you were going to plug numbers in, it would be better. If you were going to take other derivatives, or if you were going to try to find when the derivative is 0 or undefined, all of those cases, it's better to have it cleaned up. So even though we're not doing that here, eventually we're going to do that. So if there's some easy simplification, I would always do that. If it's something unnecessary, like making negative exponents become positive, then we typically don't do that at this point. So this would be the best final answer here, 40x e to the 4x squared. And then you got an exponent inside of an exponent, because the 4x is up in an exponent, and then the square is an exponent of that exponent. Okay, for natural logs, it's sort of like this. The derivative of a natural log, at first you just do 1 over the stuff. That's the main rule, is 1 over whatever the domain of it is. Then, just like this, there's 2 things you might tack on. If the domain stuff is anything other than x, then you have to multiply by 1 over that. No, I'm sorry, not 1 over, just it. Multiply by the derivative of it. And then there's a 1 over ln of the base if the base is anything different than e, or natural log. So, and then this number 17 actually has an extra thing going on at the same time, because there's a negative 4x times an ln that has an x in it. So it's actually the product rule at the same time that I'm going to do a log rule inside the product rule. So from the outside, this looks like a product rule. I have something of x times something of x. That's the product rule. So I'm doing the product rule first. First times the derivative of the second. Now here comes the log rule. The derivative of ln is 1 over the stuff. That's the main rule of it. Times the derivative of the stuff. That's the chain rule part. So the derivative of 7x plus 9 is just 7. And then there would be a times 1 over ln of e in this case, because the base of ln is e. But ln of e equals 1, so 1 over 1 is 1, and it doesn't matter. But if this was log base 5, then I would have to have 1 over ln of 5 attached on as well. So first times the derivative of the second plus the second times the derivative of the first. And that's linear, so the derivative of negative 4x is just negative 4. Okay, so I could multiply this 7 to this negative 4x and get negative 28x over this 7x minus 9. And nothing there reduces. Don't try to reduce those x's or the 28 and the 7. When there's a plus here, that prevents you from doing any individual reducing. The only way you could reduce is if you had some kind of GCF in the top or the bottom and could factor it out first. Like if this was 7x plus 14, then I could factor a 7 out, and then I could reduce the 7 into that 28. There's a plus here, but there's a minus there, so a plus, a negative, same thing as minus. And then I would put the 4 in front of the ln so that we don't confuse it as part of the log domain. You could put it in the back, but you'd want to make it clear that it wasn't part of the log. And then I don't think we need to get common denominators here. You could multiply top and bottom of this by this denominator, but it would, unless you were trying to combine this together to plug something into it, it's really unnecessary. So that could be an equivalent answer, but definitely don't need to do that here. So I've cleaned it up as much as possible. There's no very easy simplifying remaining. The 7 times the negative 4, you may as well multiply that together. Why not do that? That's easy. But getting a common denominator here wouldn't really be necessary, so why waste time and make mistakes in doing so? So negative 28x over 7x plus 9. Negative 28x over 7x plus 9 minus 4ln seven x plus 9. Okay, so there's number 17. Okay, so there was a whole chapter on just doing derivative processes, shortcut derivative rules. Then there was another chapter after that where we went into the derivative even more details about what derivatives tell us, they call that. What does the derivative tell us? So first we start with the first derivative. It tells us when original functions are increasing and decreasing. If a first derivative is positive, your original function's increasing. If a first derivative is negative at any given spot, then your original function is decreasing. So first, the only thing they cared about in this problem is when is the function increasing and decreasing? It turns out that if you take that information and look at it closer and say, well, here's a portion where it's increasing and then it switches to decreasing or vice versa, that tells you something else in addition, which we'll get to in a minute, but that's not what this problem's about. So the first thing they taught you in this chapter was when is a function increasing and decreasing? So f of x equals x to the fourth plus 12x cubed plus 36x squared plus 6. So we find the first derivative of the original function. This is a nice power rule, just term by term. 4 times 1 and decrease the exponent by 1, so that would be 4x to the third. 12 times 3 is 36, decrease the exponent by 1. 2 times 36 is 72x, and the derivative of 6 is nothing. So you find your first derivative. Anything that makes the first derivative 0 or undefined are called critical numbers, which is what they want in Part A. Part A wants to know what are all your critical numbers. Well, polynomials are never undefined, so I don't have to worry about any undefined spots here. But this is a cubic function, so there could be 3 zeros to it actually. So I'm going to factor out a 4x, GCF of 4x. That would leave x squared plus 9x plus 18. And then the x squared part might factor again. Are there two numbers that multiply to 18 and add up to 9? Yes, 3 and 6. And definitely both positive. When this is positive, then they're both whatever this is. And if this is positive in the back, then you're trying to add to the middle. Multiply to 18, add up to 9. So there are 3 unique zeros. There's 0 itself, because if you set 4x equal to 0 and divide by 4, you still get 0. X plus 3 has a 0 of negative 3. And x plus 6 has a 0 of negative 6. So these are 3 critical numbers. Critical numbers are important because they're the only places where you could possibly have a change from increasing to decreasing. So if a function has no critical numbers, which happens sometimes, that means it's entirely increasing or entirely decreasing its entire domain. If there's one critical number, then you might switch from increasing to decreasing or vice versa. Might. Critical numbers are not a guarantee of a switch from increasing to decreasing or vice versa, but it's the only chance where they could happen. Okay, so next what we do is if we want to know what sections are increasing, which sections are decreasing, we set up a number line, put the critical numbers on here in order from smallest to largest. I've got 4 sections to check. Pick any numbers in those sections. Anything bigger than 0, I'll pick 1. Anything between 0 and -3, I'll pick -1. Between -3 and -6, I would pick -4, and anything bigger or less than -6, like -7. So you need to plug these numbers into the first derivative. And if these answers are positive or negative, they'll always be either positive or negative, because they can't be 0. We already found the numbers that make this equal to 0, and these are not them. So it's impossible for any of these to be 0 or undefined. They're going to all be positive or negative. Any that are positive gives me sections of my graph that are increasing. Any that are negative give me sections of the graph that are decreasing. And that's all we care about on this problem. But on the next problem that we're also going to care about, is there a section of the graph that switches from one to the other? Then that's another special thing to know. Okay, so what was the derivative function? It was, go back to this version right here, the original version. 4x cubed plus 36x squared and plus 72x. So if I plug -7 into all 3 of those slots, I just want to know, is it positive or negative? Grab my graphing calculator. Okay. So here's the graphing calculator. It's nice because you can just type this the way it looks. 4 parenthesis -7 parenthesis raised to the 3rd power plus 36 parenthesis -7 parenthesis squared plus 72 parenthesis -7 parenthesis. So I just typed it in the way it looks. Press equals, and the answer is -112. I don't really care about the 112, but it's negative. So from -infinity until I get to -6, this graph is definitely decreasing, because the first derivative is negative in that section. And whatever it is for any one number in that section has to be the same for all of them, because it can't switch from negative to positive until it hits a 0 point. And we've already found all the possible 0 points. There's only 3 of them, these 3. So from -infinity till -6, you're definitely decreasing. And we can put that answer into part C. There's at least that interval of decreasing from -infinity until -6. And you always put parentheses here because you can't be increasing or decreasing at a single spot. You have to be moving across x values to have an increasing or decreasing going on. Okay, so then I'm going to repeat this calculation by plugging -4s into these 3 parentheses, but everything else will stay the same. This is also why graphing calculator is nice, because it's very easy to press after I've typed all this in. If I press second and the enter button, it calls up the last statement you typed in. And then with the arrow buttons, you can just move on top of the -7s and type 4s on top of the 7s, which is my next checkpoint, -4. So it goes a lot quicker in typing time too. And now it got +32. So it did switch from negative to positive. That's another idea that's taught on the next problem, I think. But all we care about right here is between -6 and -3, the graph is increasing. So between -6 and -3, I have an increasing portion of my domain. But on the very next problem, if you switch from decreasing to increasing, that's a local minimum. I basically just did the first derivative test right there between these 2 answers. If your answer switches from negative to positive, that's a local minimum. If you switch from positive to negative, you have a local maximum. So we didn't really care about that on this problem, but we ended up showing that that was the case. So now I'm going to plug -1s in, and maybe it's going to switch back to negative. Often on these polynomials, that's what happens, is that each time you get to a new one, it switches, but you're not guaranteed to always switch to the opposite one, especially if you get more complicated functions. So second enter and plug in -1s into the 3 -4 slots. I just changed all 3 -4s to -1s. And yep, it switched back to negative. Now it's -40. So it switched from positive to negative right at a critical number. That's got to be a local maximum right there. And then finally, I'm going to plug 1 in and see if it switches back to positive, which it usually does with polynomials. So now just go right on top of the -1s and hit the delete button and delete the negatives is the easiest way to type it. Delete the negatives, and then you don't have to retype the whole thing. So I deleted the 3 negatives, and now I just have +1s in all those locations. Enter. Yep, it switched back to +112. So we went from a negative derivative to a positive. That's another local minimum. So even though this problem doesn't care about it, there's 2 local minimums and 1 local maximum on this. In fact, if you have college algebra knowledge, x to the 4th graphs often look like a W. They kind of look like this many times. So it makes sense that there's 1 local maximum and 2 local minimums. And the local minimums may be at the same place, y value-wise, or they could be different y values. Sometimes there's like a total symmetry of the graph, and it literally looks like a W, like that. But sometimes it's like off balance, and it looks like this sometimes. We don't really care about that right now, but there is a section at the end of this chapter where you care about the graphs, and then this kind of knowledge can help you. Okay, so I went from decreasing to increasing, then I had another decreasing section between -3 and 0. So I need to add that as another answer. You put a comma here, and then from -3 to 0 is a second section of decreasing. And then it turned out there was a second section of increasing from 0 all the way to infinity. And also a key thing is that all the answers in part B and C, the only thing that should ever appear here are infinities and critical numbers. So notice all my answers here are -6, -3s, and 0s. Make sure you're using whatever you said part A numbers were in your answers. A very common brain cramp that anybody can make is where sometimes they put these numbers in their answers because they were working with them. It's easy to forget you're just using these as arbitrary checkpoints. So I often like to cross them out when I'm done with them so I don't accidentally put them in my answers. So it should only be the critical numbers that go in the answers. And problem 18 only cares about the increasing and the decreasing. It doesn't care about local max or min yet. I think that's coming up on the next problem. Yeah, see here it says find the x values of all points where the function has relative extrema. Extrema is the generic term for local max or local min if you don't care about which one it is. Find the values of any relative extrema, that's the y values. So they want me to get the x values and the y values of them. Okay, so 19 starts off similarly. We have x to the 4th. So there could be 3 critical numbers. Minus 18x squared plus 81. This is one that might be a symmetrical graph that looks like a W actually. So the first derivative would be 4x to the 3rd minus 36x to the 1st plus nothing. So this is never undefined because it's a polynomial. It could equal 0 3 times. I'm going to factor out the 4x again, leaving x squared right there. And that would leave minus 9. And that's a difference of squares. That factors into x plus 3 and x minus 3. So we do have 3 unique zeros of the derivative. So 3 unique critical numbers. There's 0 itself. There's -3. And there's +3. So I'm probably going to get a very similar thing happening on the number line here. -3, 0, and 3. I would pick -4, -1, +1, and 4 as my checkpoints. So I need to plug into f prime. I need to plug in -4, -1, 1, and 4, and see if these switch from positive to negative or vice versa. So plug them in right here into the main derivative function. 4x to the third, 4 parenthesis, -4 parenthesis to the third, minus 36 parenthesis, -4. So this is how I'm typing it in. The answer is -112. So what we know so far is we're decreasing till we get to -3. Then if I press second enter and change the -4s to -1s by just typing over the 4 with a 1, the negative's still in there. Now it's +32. So it just switched from negative to positive. So that switched from decreasing to increasing. That's a local minimum. We have a local minimum at x equals -3. There is probably going to be 2 local minimum. Okay. So at x equals -3, there's one of the 2 local minimum. And the value, the minimum value of blank, I'll figure that out in a minute. But let me get all the mins and max first. Okay, so next I'm going to plug 1 in by hitting second enter and deleting the negatives so that I just have 1s there. And now the answer switches back to negative. So right there, there's a local maximum at 0. So -3 is a local minimum spot, and 0 is a spot where there's a local maximum, relative maximum. Relative and local mean the same thing. Okay, so then second enter and change the 1s to 4s. Oops. And I'm guessing it's going to switch back to positive. Yes, +112. So then at 3, there's another local minimum. So just because I knew this was shaped like a W is how I knew that was going to happen. So there was a -3 and a +3 local minimum, and there's a relative maximum at 0. That's as much as we did on the previous problem too, basically. Now they want the actual y values of all these 3 spots as well. That's when you plug back into the original function. The y values of the extrema are from the original function, not from the derivative function. In fact, if we plug these 3 things into the derivative function, we would get 0 for all 3 of them because they were the critical numbers. So it wouldn't make sense to plug them into the derivative function anyway. So plugging 0 in is very easy because all this disappears and you would just get 81. And then the 3s and the -3s are going to give you the same answer because the exponents are all positives. So I can just do 3, and whatever I get, it's going to be the same value for both of them. 3 raised to the 4th power minus 18 times 3 squared plus 81. So the value for 3 is 0, and therefore it would be the same thing for -3. Now there could have been 2 separate answers here. Then you'd separate them with a comma, but I don't believe you would put 0, 0 here. You don't write the repeated 0. So this is one of these W shapes that would be symmetrical like this. And in fact, these 2 local minimums are touching the x-axis, is what's happening. So this is the coordinate -3, 0 right here. And this is the coordinate 3, 0. And this is up here at 0, 81. This is the 2 sections in this chapter from now. 2 sections away is a section about graphing using all this calculus knowledge. So that's what helps, is I can know exactly these 3 spots on the graph. and they happen to be all also intercepts, which isn't always the case, but especially when they're not X or Y intercepts, then they're points that students in algebra would never know. Here, algebra students might know these points just because they happen to be intercepts too, but the power of this is really when they just are random points somewhere on the graph, and the algebra student would have no way to know what those points are because they don't know how to do derivatives. Okay, final problem for this second of 3 videos is in the section after that one, we learned about the second derivative and what the second derivative tells us too. So in a very similar fashion to the first derivative, anytime the first derivative is positive, your original graph is increasing. If your first derivative is negative, your original graph is decreasing. And if it ever switches from positive to negative or vice versa, those are special points too. Anytime the second derivative is positive, the original graph is concave up and it has an upward curvature. Anytime the second derivative is negative, the original graph is concave down with a downward curvature. And if you find spots that are similar to critical numbers, any numbers that make the second derivative zero undefined are places where you can get what are called inflection points. And that's where the concavity switches from up to down or down to up. And unlike the first derivative, where there's a different name for both of those, local max and local min, we care which one's which in the first derivative. In the second derivative, there isn't any distinction between what if it's concave down first and switches to concave up second, or vice versa. They don't have separate names. They're both called inflection points. Okay, so number 20, the original function is a cubic function. And it's negative 2x to the third plus 3x squared plus 166x minus 2. So I'm going to take the first derivative, which is negative 6x squared plus 6x plus 166. Now, if I was doing the full process of the next section where the graphing part is, I would have to get the critical numbers from that. There could be 2 critical numbers there. Right now, I don't care about them because I'm only caring about the concave up and concave down part. So I can go straight to the second derivative then and get negative 12x plus 6. And the derivative of that is nothing. So this is linear, and it's a polynomial, so it's never undefined, but it could equal 0 once. So because it can equal 0 once, there can be 1 inflection point to this problem. Could be, not guaranteed to happen. And divide by negative 12, x equals a half. So an x value of a half is the only place where there might be an inflection point. So by a very similar process to what you do with first derivatives, if I put this on a number line and pick one number smaller than that, one number bigger than that, and plug them into the second derivative, they're going to be positive and negative for sure. They could be both positive or both negative or one of each, but they can't be 0 because this is the only number that's 0. So if I plug in 0 and 1 into the second derivative, I'm hoping that one's positive and one's negative, and then I'll get an inflection point. And here we don't even care which one happens first. So if you plug 0 into right here, you'll just get 6 for the answer. So the graph is concave up first. The graph will be concave up all the way till you get to 1/2. It'll be bent like this. And it may be increasing or decreasing, but it's definitely concave up. And then when you plug 1 in, negative 12 plus 6 is negative 6, so then it does switch to concave down. So that's going to bend the other way like that, and this is an inflection point then. It's switching from concave up to concave down. And that's all we really care about here. So it's concave up first from negative infinity till a half. And then it's concave down after that from 1/2 to infinity. And because it did switch from one to the other, there's an inflection point at 1/2. 1/2 comma something. And they do want an ordered pair, so that means they also want the y value. Y values are always from the original function. So I have to plug this 1/2 not into the second derivative, not into the first derivative, into the original function. -2 parenthesis 1/2 raised to the third power plus 3 parenthesis 1/2 squared plus 166 parenthesis 1/2 minus 2. So I got 81.5, which I can hit math, enter, and make it 163 over 2. 163 over 2. So that's all you care about on this problem, is when is it concave up, when is it concave down, did it switch from one to the other? Yes, then there's an inflection point there. And you don't care which one happened first. Now, with your college algebra knowledge, you might know that this has a negative leading coefficient, and it's an odd degree. So like in the first video, problems 1 through 10, there was a couple of problems about end behavior. That's where it rises on the left and falls on the right. Cubic functions can look like this, where they come down and then bend up and then bend back down again. So what's probably happening here is this is the concave up portion right there. All of this is curved upward. And it actually goes past the local minimum. The local minimum's here, and then past that, that's where the inflection point is. So the inflection point is at 1/2 and 81.5. I'll just put 81.5 for purposes of understanding it better. And then the local minimum is here, whatever that happens to be. There's a local maximum there, but that's after the concavity switches. The concavity switch is often at a different place than where the local max and mins are. So that's basically what happens. You have this big concave up portion to about here. And then after that point, then you have a big concave down portion. And there's your end behavior, up on the left, down on the right. There turns out there's also a local min and a local max, which we would also do in the next section. In the graphing section, we would care about all the stuff of the whole thing, but here we're only caring about the concavity and the inflection point. And so there's that inflection point. And that's a key point in business too, to get your point of diminishing returns, where if you advertise too much, you're just wasting money. Okay, so this video was just slightly less than an hour for me to do 10 problems, although again, I'm doing a lot of explaining at the same time. If you were just working these out yourself, you could do them in less than an hour. So 2 hours for the entire review, 2 hours for the entire final is probably more time than you need, but at least you'll have a full 2 hours and not to be rushed. I'm going to submit this and see if we got all 10 of these right between 11 and 20. If I get a 33.33, that means I got them all right. So today I didn't do any brain cramps. And 11 through 20 are all green checks. So if you did this on Tuesday with this video, then you're on a good pace to get a good grade on the final. On Wednesday of the exam week, we're going to be doing problems 21 through 30. And then Thursday and Friday, you get 2-day window for taking the final, but I would make sure you do one more run of the review. Sit down one time and do all 30 questions in one sitting. Give yourself 2 hours. Put a timer on yourself for 2 hours. Try to do all 30 problems in 2 hours. Submit the review at that point, and if you get a good grade, then you're going to know that you're probably going to do well in the final, in addition to getting a good grade for the review. And if you can't get a good grade doing that, then that's a warning that you're not ready for the final. So it's better to know that in the review than to find out in the final that you weren't ready for it. Okay, so that's it for the second of 3 review videos. There's one final video for this semester that will cover problems 21 through 30.